Welcome to part 4 of section 3.2 where we delve into the factor theorem. The factor theorem is pretty simple. We actually talked about it in the last video at the end. If p is a polynomial, then any real number c is a zero of that polynomial if and only if x minus c is a factor of that polynomial. So the zeros and factors really go hand in hand. So if x equals 7 is a 0, then x minus 7 is a factor. And if, let's say, x equals -1 is a 0, then x plus 1 would be a factor. All right, in our first example, we want to know, is x equals 2 a 0 of this polynomial, x cubed plus 8? Well, if you plugged in 2 here, we don't get a 0 out. But we can kind of prove this. We can see this using the remainder theorem. So I'm just going to double check and use the remainder theorem. I have a 1x cubed, I don't have a quadratic, I don't have a linear term, and then I have a constant term of 8. Looks kind of weird, looks like binary a little bit. Bring down the 1, 1 times 2 is 2, 2 times 2 is 4, 0 and 4 is 4, 4 times 2 is 8, and we're so close, but they don't cancel. We end up getting 16. So is x equals to a 0? No, it's not. We also know that since x equals 2 is not a 0, we also know that x minus 2 is not a factor of our function. So this is kind of proving it in the other way. So since x equals 2 is not in fact a 0 of this function, it's not an x-intercept, we know that x minus 2 can't possibly be a factor of this polynomial. Let's take a look at an example where we do have a 0. All right, we're asking now, is x minus 1/2 a factor of this long quartic polynomial here? So we want to know, is this a factor? We're really asking also, is 1/2, positive 1/2, a 0? So let's check using synthetic division. 1/2 is our number in question. We want to know that when we divide p of x by x minus 1/2, we want to see what remainder we get to see if 1/2 is in fact a 0. So let's see if we're skipping any terms here. We have our quartic term, cubic term, quadratic term, linear term, and constant. We're not skipping any, so no 0 placeholders necessary. All right, and then we'll do synthetic division. Bring the 4 down. 4 times 1/2 is 2. Combine here, we'll get a -2. -2 times 1/2 is -1. Combine to get a -12. -12 times 1/2 is -6. 12 and -6 combine to a +6, and 6 times 1/2 is 3. So we end up getting a remainder of 0. So again, according to the remainder theorem, this tells us that p of 1/2 is 0, meaning the coordinate point 1/2, 0 is on p of x. 1/2 is a 0. So we know, we'll do this instead, we know, in conclusion, or thus, x equals 1/2 is a 0 of p of x. And so x minus 1/2 is a factor of p of x. So we know that p of x could be broken down into x minus 1/2, and then this remaining cubic polynomial, which looks like 4x cubed minus 2x squared minus 12x plus 6. And of course, we don't need to write the remainder of 0 there. To be a factor means you fit in evenly into something. You know, I gave the example in the previous video of the factors of 10 are 1, 2, 5, and 10, because those numbers divide into 10 evenly. We would say that 7 is not a factor of 10. Even though 7 fits into 10, it doesn't fit in perfectly. There's a remainder of 3. And so when we say something's a factor, it means that there's no extra. There's no remainder. It fits in perfectly. So x minus 1/2 is indeed a factor because there's no remainder when we divide by x minus 1/2. And we do that by testing the potential zero of 1/2, the x value. In conclusion, if we divide p of x by some linear binomial x minus c, and we get a remainder of 0, then we know that x minus c is in fact a factor, and x equals c is a 0. So once again, the factor theorem just kind of hammers the point home of the relationship between zeros and their corresponding factors, and the factor theorem and remainder theorem are tied heavily towards one another. I didn't really give a ton of new information in this video. I'm just, again, talking about the importance of zeros and the relationship between those zeros and their corresponding factors.